Good afternoon, everyone. Thank you, Mr. Chairman, for introducing my presentation. My presentation topic is dealing with damage evaluation of aluminum alloys under cryogenic and irradiation conditions. My presentation is composed of mainly 5 parts. The first part, introduction, motivation, and background of my study introduced, and the second part, extended damage model developed in and constructed in this presentation will be introduced. And the following 3 steps will be introduced. Introduction. As all of you knows, advanced nuclear technologies such as nuclear thermal propulsion, fusion, or in challenging stage focusing on operation longevity and high energy efficiency. Although, NASA's DRS-5 entity considered as a key technology because of the long distance and extreme space extrapolation, such as mass exploration by using a liquefied fuel, liquefied hydrogen, and coolant. However, this liquefied fuel and coolant has an inherent design constraint such as cryogenic and high energy irradiation surround embedded in reactors. So, although aluminum alloy have been considered as a candidate material of nuclear tank because of the high ductility against the cryogenic temperature, however, high irradiation may cause a reduction of ductility of aluminum alloys. To solve this problem, mainly researchers consider the 2 type approaches. First, the experimental approach, such as global test using a more possibly generating higher energy radiations. However, this method is time-consuming and requires many monies. So limited data were reported due to the practical issue around the safety concerns and the particle issue from the high energy irradiation especially in Korea. And the alternative method, damage mechanics, was continuously developed and revised and expanded to widely applying micromechanism of fracture such as void recreation, growth, and necking, and coalescence and reaching to the fractures. These equations, as you know, modified GTM models and the 9-parameter approaches and the Lossell model 2-parameter approaches. However, this using a conventional GTM model and Lossell model to consider the cryogenic and the irradiation effect in case high numerical cost may require to calibrate in case by case material parameters. So to solve this problem and construction, I set up the 3-step objectives. Firstly, extended damage model considered cryogenic and irradiation condition was constructed, and then calibration microscopic parameter of extended damage model set up this presentation. Incorporate comprehensive algorithm such as Latin cube sampling. Finally, estimation of flex toughness through the cross simulation incorporating damage models. And finally, ASTM standard was also incorporated to evaluate the J integration. This step is extended damage model. I will introduce my methodology. In my studies, model extension method is based on the GTM modified GTM model. As you know, its potential is depicted in these equations. Among the parameters, I firstly consider the initial porosity on the cryogenic irradiations. Previous studies already detect on the cryogenic and the specific dose and the radius of the cluster, and using these data, I calculated the ideal sphere porosity fraction of the initial porosities. And additionally, empirical calculation of nuclear irradiation was basically set up to dpa. Our second step is a combination of specimen model. As you know, a porosity lace is composed of mainly two parts. First, the nucleation part and plus growth part. In my study, porosity nucleation considering a cryogenic was embedded using empirical data-based regression equation. And you see the desiccation. If you're using a desiccation, this can be reflected the specific cryogenic conditions. And then porosity growth term was added, was revised through these binary terms. This term is expansion rates of cross radius on the cryogenic and the irradiation. The key feature of this term is the relations of activation energy and the temperature relationship between the shear stress and the applied stress. Using these equations, I constructed the user subroutine for coupling with the numerical analysis tools such as Abacus with the Fortran basis. This presentation chapter represents the calibration method of material parameter of my extended model. As I mentioned, damage calibration is request of many numerical posts. For reduction case, I adopted a complementary analysis algorithm, calibration metrics such as Latinapa cube sampling. As you see the below pictures, I performed 100 cases analysis through the 3 steps. As you know, first step has a good large variation, and 3 step has minor variation. From to 3 step analysis variation and the median and the optimal result can be concluded. Target data of Tesla simulation is reference data from the Japan and the Lewis theory. Analysis condition is corresponding to the experiment method. Specific information as this information was embedded in summarized in the table. A calibration result. Through the 100 analysis, I determined the certain parameters, pre-mentioned these parameters, and as you see, using a fundamental material inputs, strength and elastic modulus, and calculating extended GTM model inputs, I performed the tensile stress strength, the simulation using the opted bar, and this is for my set distribution, and this is the porosity corrections according to the stress concentration, and the porosity correction was reached to the parallel porosity lace. The parallel was simulated. Please see these figures. This is the calibration data. Triangular symbol represents the experimental data, and the blue line is presented to my simulations. An additional 3 analysis was performed considering room temperature and virgin materials. These 4 chapters represent the correct growth in analysis using the verified extended model. FA model was constructed in the dimension of 3D, and the material is aluminum 66T6. And the standard CT specimens were constructed and optimized the mass optimization. The pre-particle crack was embedded in the central line of the CT specimen. Element size of crack propagation regions was the same with the notched, pre-mentioned notched. This is another result. On the cryogenic, 77 Kelvin and irradiation conditions, 10% dph. As tensile load was reached to the specific values, the crack growth was simulated, and the porous fractions distribution also you can confirm. Additionally, room temperature and virgin condition was also applied. Please see the simulation videos. you can see the porosity growth and the creation and the failure. Using this simulation result, I also calculated the gel estimation to calculate the fracture probability, fracture toughness. Firstly, gel curve estimation was performed using a P delta curve and incorporating ASTM standard and conventional this equation J integral based on the P delta curves on the areas. The qualification as a fracture toughness was also performed. Consequently, JQ was conformed to J1C fracture test. As summarized, please see these two figures. The left figure was concerned of cryogenic condition. The right figure represents in the room temperatures. Generally, in the irradiation condition and the cryogenic condition, which was slightly lower fracture toughness, and otherwise, room temperature and the virgin material was higher fracture toughness in the room temperatures. I will summarize my presentation. In my presentation, material damage on the cryogenic and the irradiation conditions were preliminarily evaluated using a numerical model, reflecting micromechanical features using a GTM-based and the complementary algorithm, Latin cube sampling. Firstly, numerical-based P data curves were compared with the test data on the cryogenic and the irradiation conditions. And secondly, in the scope of present study, in generally, cryogenic effect was more dominant to the damage than irradiations. Lastly, reduction amount of fracture toughness J1C value at the room temperature and the cryogenic conditions were predicted to 30% and about 4% respectively. And as a conclusion remark, the extended GTM model can be utilized by the combined reliable data with the incorporating time and the numerical cost and the financial effects, combining or technical approach to assess the other degradations mechanism on material, such as long-term aging through the operation of a nuclear power plant and the hydrogen enrichment and in the future hydrogen liquefied tank and the antifreeze coolant tank. Thank you for kind attention.